Okay, so I wanted to talk about, I wanted to do one merge sort problem as a review. And I wanted to do just one, add a little bit to the linked list code, and then talk about a new algorithm called QuickSort. And QuickSort it's an important algorithm, but it doesn't actually take a long time. It's no more complicated than merge sort. So these are these two important algorithms that really are, there's really not a lot, there's not a lot of steps. There's not a lot of places to go wrong where, sometimes these algorithms, there's a lot of steps and there's a lot of, there's a lot of room for error, but the merge sort is, they're both very straightforward. And the code actually isn't long for either one of them. So why don't we just start with merge sort? And so this is from an old quiz. And why don't we just, let's see here. So I'm going to share the screen and wait a second. Hold on. I see my grade book is open. So let's just hold on here. I apologize. I should have had this shut down before okay, so I cannot, okay, so let's see here. Hold on, students. Let me see what's open here. And yes, I see. Okay, yeah, no, it was actually, okay, no, there actually weren't any grades showing. Okay, so let's try this again. There actually weren't any grades showing. I just saw a tab at the top that said instructor gradebook. So that's not good. Okay, so I want to, okay, so let's share the screen. And okay, so now there should be, I should see this file. So we're looking at a bunch of files right now, or just these icons. So let's just look at this. So this is from a quiz that I gave actually almost, it says spring of 18, so it'd be like 3 years ago. So I'm trying to remember. It seems like a long time ago. I can remember 2 years ago, but not three. I don't remember who was in the class. I guess I could look at my roster. Okay, so why don't we start, and then, yeah, so there's actually two merge sort problems on this quiz. They're pretty similar to the worksheets. And if you remember this merge sort really actually there's two parts to merge sort. What we're talking about is we're talking about the merge part of merge sort. So we're taking two pre-sorted arrays and then combining them. So there's actually another part which guarantees that the left half and the right half is sorted. So there's one part where, maybe you have an unsorted array like BA, and then I know, let's say like S and Q. And so what you would do is you would actually merge those two and then those two, and then you have A, B, and then, well, actually now that's sorted. Let's do it the other way. So let's say you're asking this algorithm to sort. So let's say you want to sort SQ and B and A. So it's really very unsorted. So what would happen is first you would merge those two together and get Q and S. And then you would merge these two together and get A and B. And now you can merge the whole thing together. So there's that one part where you break the array down into smaller and smaller pieces until you get these arrays of size 1, and then you merge the arrays of size 1 to get an assorted array of size 2, and then you merge the arrays of size 2 to get a sorted array of size 4, and so forth. That's the recursive part. All we're worried about is the merging, because it takes too long to actually write out the entire solution. Okay, so let's say, how are the keys RKX merged with the in-place merge method? Okay, and so what we can see here is that so we can see here that the left half is sorted, right? So we have R and X, and then we have K. And so remember, what we do here is, in the merge method, we keep two copies of the array. So there's the original array, there's this array AUX, like here we have A and AUX. And so what we're doing is we're actually writing over A. So like our A would be RXK. And every iteration, we're actually writing over an element. First, we're writing over first iteration, write over element 0, and then write over element 1, and then write over element 2. And then what we have, and then there's we keep a copy of the original array. Okay, and so that would be like this part up here. So whenever we do the comparisons, make sure we use the original array. And I've done that lots of times where I haven't because I'm going too fast. And in every iteration, so what we do is we just start, so the left side starts at 0, and the right side starts at 2, and we're always, and that's J. So the I starts out at 0, the j starts out at 2, and we're always comparing, every iteration, we always compare less a sub j, a sub I. We're always comparing, so if what's on the left side is less than what's on the right side, we copy the element on the right side to the latest position. Otherwise, if there, and if a sub I is greater than or equal to a sub j, we take what's on the left side. So basically, so the first time, what we're doing is we're going less. So I is 0 and j is 2. We'd basically be going less, I'm sorry, k comma r. So a sub 2, so we're comparing a sub 2 and a sub 0. So a sub 2 is k and a sub 0 is r. So this is basically what we'd be doing. And we know that k, that's true. K is less than r is true. So you place the k in position 0. We'll look at the type version in a minute. So you put so in the first iteration, we put that k at position 0, and then the rest of the array stays the same. So you get 2 k's. So what would happen is that you're really writing over the original array. So that r in the original array would go away, and that would become a k. And so what happens to that r when you need it? That's why we keep another copy of it, right? Because if you didn't keep a copy of it, and then we've lost that r forever. Okay, so then in the next, so then what happens is we used a value from the right side. So this is, so I equals 0, that j equals 2, that's what we use for iteration 1. Now let's get ready for iteration 2. I stays at 0. J has become 3. We took one from the right side. So when that happens, that means just use for the remaining iterations, right? This has gone, j equals 3, we've gone over the edge. So just use the remaining elements from I. So why don't we actually look at the typed version? Okay, if I can find, okay. And then we'll go back. Okay, so look what here, so the very first iteration, we compared R and K, so the K went here. Okay, so then the second iteration, okay, so J is now 3, right? So before iteration 1, I was 0 and J was 2. And then after iteration 1, what happens? We increase J by 1. So every iteration, you're either increasing J by 1 or I by 1, but never both, and they never go down, right? So either one or the other changes. And okay, and so now we use J equals 3, right? Because so the left is positions just 0 and 1, and the right is just position 2, right? There is no index 3, right? So J is actually now equal to the length of the array. That means we've used everything from the right side. So the remaining iterations, we'll just use whatever remains on the left. And we actually haven't used R or K or X. So the second iteration, you place R in column 1. And in the third iteration, you place the X in index 2. Yeah, so every iteration, we're just gradually building up this sorted array. So if you look after iteration 1, you can underline it. It's definitely the smallest. Iteration 2, K and R, those are the next two smallest. And then it's completely sorted. And then in the very last, we'll see this more. In fact, let's actually we'll do that for problem 2. But so any questions so far? Otherwise, I'll go back to, I'd like to just go back to we'll do this problem right here. Let's just do one iteration on the other notes right there. So, okay, let's just do problem 2. Okay, the one thing is, okay, so what happens here? So the I points to the first, the left boundary of the left side, and J is initialized to the left boundary of the right side. So the J is right here. And so I is 0 and J is 4. And okay, so initially we're going to compare, we always compare is what is the element is A sub J less than A sub I. Okay, and when we're done, we have to have looked at every single character, right? Right. So we can actually fill in this last cell right away. Okay, so when we've looked at every character on the left, that means your I is 5, right? I is at the beginning, right? Is it? No, I'm sorry. No, it's 4. I'm sorry. we've looked at every character on the left. I is the initial j. So I'll just write it down here, it'll be a little bit easier. So I is 4. So when we're done, I better be 4, right? Because the y is because the I consists of 0 through 3, and the j consists of 4 through 7. Okay, so when we're done, I is going to be 4, and then the j is going to be 8. I will be at the we'll actually be in the first element of the right side, and the j will be will actually be equal to the length of the array. Right. So we've gone one past the left side, and the j we've gone one past the right side. So you can actually fill this last cell in right away if we want for the I and the j. Okay, so again, so we initialize I to 0 and j to 4. So that means, so before the first iteration, that's the value of I and j. So during iteration 1, we compare a sub 4 and a sub 1. So the first iteration compares a sub 4 and a sub 0. And we take the smaller of the two, and if they're equal, we take what's on the left, right? Okay, so we know that a is less than b, so you would write an a here, and we're writing right over the array, so the rest of the array stays the same. And we used a value from the left. I keep saying left, I mean right. We used a value from the right side, so that means, okay, we're done with position 4. Okay, so as we start iteration 2, as we're about to start iteration 2, well, I will still be at 0. We actually haven't used that b yet. We haven't used the b in the very first column. We used the a that was in index 4, and now the j points to the d, because we're merging these two. So now we ask ourselves, we're going to compare 5. We're going to compare the b and the d. Okay, so we compare the b and the d, and it turns out b is less. And this will be the last one I'll write. We'll look at the typed version. It's kind of bad. So it's ab. And then the rest stays the same. And notice that so we're gradually building up this sorted list. And so, and then which one, we chose the b from the left side, right? The b from, we chose, so we're done with this, that one from the left. So increase, so that before we start iteration 3, I will be 1 and j will be 5. So why don't we look at the typed version of this? And I didn't actually highlight the changes in bold, but if you look here, so what happens here? Iteration 1 is the absolute smallest. Iteration 2 is the second 2 smallest. And then everything above is the same. First 3 smallest, first 4, first 5, first 6, first 7, and then the whole thing is sorted. And everything above, like this main diagonal, is just the original array. So that's when I first started giving this problem. A lot of times students wouldn't follow me at first. And then all of a sudden, it's, oh yeah, I see it. Everyone saw just about everybody saw the pattern. And I wouldn't really give a lot of points to this problem because it was just so, the pattern, you can actually feel, anybody could do this without, they just notice this pattern here without really understanding the algorithm. Just noticing the pattern, first smallest, first 2, first 3, first 4, and everything above the main diagonal is the original array. We don't really know what's happening is that we're comparing the left to the right, or comparing an element on the right to an element on the left. So that's when I added, what are the values of the indices on the right and the left? But even that's not so bad. You just ask yourself, which side did I take it from? You took the a from the right, so you increased the j. Here right? So the second iteration, you took the b from the left, so increase the I. So even that's not too bad either. So most students, almost every student, at least when I taught in the class, got this. And maybe about half the class got this part. So, but the one thing to know is common errors that I saw. Some students were increasing both I and j. So from row to row, you're either increasing I or you're increasing J, but never both. And there's always one of them that's being increased. So if they both stay the same, that's wrong. If both I and J are increasing, that's wrong. And they never decrease, right? And again, the very last value has to be what's the last value of the last value of I and the last value of J? Well, you just have to ask yourself, it's always one more than the last index of the given side. So the I's are 0 through 3, the J, right, 4, right? So 0 through 3 is I, and then 4 through 7 is the J's. So I has to be one more than one more than the left side, which is 4. The J's have to be one more than the great one index more than the right side, which happens to be 8. So we can actually, as I said, fill that last row in right away. But when I see that last column wrong, some people go like 9, J equals 9. Well, the length is 8, so it can't be 9. I mean, the indices are numbered 0 through 7. So, and I'll look for another quiz problem that you can try. So a problem like this will be on your quiz, and then I guess I would ask, you might do the same thing where you just create a Word file or just draw it by hand and upload a photo. We'll see. Okay, so are there any questions on merge sort? So yeah, a problem like this will be on your quiz on Monday. Yeah, I was talking about a quiz today, but I decided that we weren't really ready for a quiz yet. I wanted to go over this again. Plus, there wasn't maybe just wasn't enough to put on the quiz. But yeah, the next quiz will have merge sort and quick sort. It's pretty exciting. No questions on merge sort right now, but you can always ask later. It's pretty intuitive, I think. I mean, it's a widely used algorithm, and it's very intuitive. It's really not a lot to it. So, students, why don't we talk about? I'd like to talk about. Now, you should see Eclipse at this point. And one thing, let's just remind ourselves. Maybe let's take about 10 minutes to talk about linked lists, and then we'll talk about QuickSort. Let's see if I can just open this up here. Oh, is it opening? Thought it was. Oh, here we go. Okay, so let's just look at this link. Yeah, it started working again. I don't know what happened. So remember the linked list? You have these node objects. And in the way we wrote it, you can either have a singly linked list where you can go from left to right, or you can go both, like a one-way street. So let's say here's the head. So we know where the head is. And then if we have a doubly linked list, we know where the last node is. That's all we know. We know where the first node is or the last node is. So the next after last is null. And the one before the head, previous, is null. And the whole point is in every node object, we're keeping some kind of data like a string or something like, cat or a or, 2, I don't know, is, okay. So there would be, maybe we'd be storing strings, but just any kind of object. So that's basically what it is. And so last time we learned how to add to the end of a linked list. And if there's only one element in the linked list, the head and the null, no, if there's only one element in the linked list, only one node, head and last are the same, right? And if there's 0 nodes in the linked list, then head equals last equals null. Like there's nothing there. Head and last are null. So head and last are null, or correspond to size being 0, right? So in this case, there actually is an instance variable size. In this case, for my drawing, size would be 4, right? Because there's 4 nodes. Okay, so why don't we actually go to the code? And so we actually have, this is what we did last time. So remember, so we have the linked list object as 2 instance variables, head and last, because this is going to be a doubly linked list. We'll keep track of the number of nodes. So we'll have a private instance variable called size, just like array list has a size. And all the methods, just about all the methods that we learned or we use in array list are available in linked list. Okay, so as we just saw, that the linked list consists of a bunch of node objects linked together. And the user of our class doesn't have to know about nodes, right? Just like we use array list in Math 130, but we use it without knowing that really underneath it is an array that can be somehow kind of be artificially be expanded. But we can, but that doesn't mean we can still use the array list without knowing all the details. Underneath, just like I use my car, I turn my car on, I turn it off, I really don't know what's going on. So, so anyway, each node, right, it's a private class node because only the linked list class needs to know about nodes. So we have this private class, which is kind of probably the first time we saw that. And yeah, so it has an instance variable item, that's what's being stored. Instance variables node and previous, which is the node to my left, which is the node to my right. And a constructor that updates the item, what's actually being stored. Okay, so let's look at the, remember the add method? Just like we have an add for link, no, array list, we want to add a new node at the end. Okay, so the user puts in the item like add cat or add dog or whatever their favorite string is, and add is the only time we actually go new node. And so what we're doing is we're just passing the user, I can't write in this, we're passing the user's data to the constructor. So we get this node, so the item instance variable is assigned a value. And then we just, again, last time, if head is null, if head is null, then this new node is both the first and the last. Otherwise, we just make it the last node. So what I'd like to do now is, well, first of all, let's just write a couple of methods. The easiest one to write is public. Whoop, that's not going to be good, is it? Okay, that's not good. Okay, so let's say we just get public int size. So just like we have a size method in just like we have a size method in the array list class, we have one in the linked list class. It just returns the size instance variable. Okay, that's useful for loops and looping over an array list. Or a linked list, also array list. Let's actually try get. Let's just try this get method. Okay, so I don't need this right now. So we're actually going to get, we're going to put some exception handling in there. So public e get int index. And what we're going to do is return the data that's stored the node at position index. So these nodes are numbered. So this would be, it's just the head would be 0, the one after the head would be 1, 2 after the head would be 2, 3 after the head would be 3, and so forth. Okay, so just like array elements are numbered, head will be the first one. Head dot next head is position 0. The one directly after head is node 1, and 2 after the head is node 2, and so forth. Okay, so we're going to get the data stored at position index. The first thing we want to make sure is that our index doesn't go out of bounds. So we want to make sure the index is positive. So we're actually going to put in some error handling here. So if index is negative, well, you can't have a negative index, or we can't get what it's like an array list. You cannot get what's a position size. So if there's 10 elements in an array list, they're located in positions 0 through 9, just like an array. And we're going to do the same thing here for linked list. So or index is greater than or equal to size, because we can't get. So again, if size was 10, the biggest index that we can get is 9. The biggest node number is node 9. So in here, you can explicitly throw new index we can actually force this exception. And so what that does is we can write a main method, but what that does, it actually, when we get an error like index out of bounds or null pointer exception, an object is actually being generated. And we can actually use that object to have our code kind of, end gracefully instead of just crashing with that kind of DOS window. We talked about that a little bit, though we're actually not being tested on that. But yeah, but there's an example where we're explicitly throwing an exception. Okay, the get method, we're writing the get method now. That's great. All right, get method. Okay, so we're going to have a loop here. So let's just start. So we actually want to iterate through the, we're going to iterate through this linked list. And I'm sorry, I keep going back. And as I said, if I had a whiteboard, or maybe I knew how to use Zoom better, I could do this. But what happens here is that you start the pointer we're going to start, we're going to create this node variable and put the pointer here. So the one right after, if the head is called pointer, the one after pointer is pointer.next. So if the node that stores cat is pointer, the node that stores a is pointer.next. So we're going to take advantage of that fact. So let's just create it, define a node object. We'll call it PTR, and that's going to be the head. So and you're guaranteed that size is 1 at this point, right? So let's say size was 0. Okay, well, if the index is negative, you'd throw an exception. But let's say the size is 0. So everything is either less than 0 or greater than or equal to 0 is basically what I'm saying. So like there in line 20, if you replace that size with 0, that Boolean expression is automatically true. A number is either less than 0 or greater than or equal to 0. That's true of every number. Okay, so so then you would throw the exception and the code, this method would just end. Okay, so if you get past that if statement, you're guaranteed that size is at least 1. Okay, so node pointer's head. And then now we're going to iterate through the linked list. So for int I is 0, I less than index, hello, I plus plus. And all we're going to do now is we're just going to say, oh, let's move the pointer to the next node. This is kind of the classic way, that line 24 through 26, that's the classic way of iterating through a linked list. And I know that'll take me to the correct spot. Let's say index is 1, right? 0 less than 1 is true. So you would iterate 1 time. You would move to the next, and you'd start at the head, and you'd move, then you would do this. Every time you execute that loop in line 24, you're advancing to the next node. So if index is 1, that would have 1 iteration, right? And so you actually would advance to the node directly after the head. So this actually will take you to the correct place. And then what do we return? So when we're done, pointer points to the node that contains the data we want. So now you just return pointer.item. And that's it. So advance to the correct node. So advance to node number, to node index. Okay, I'm not sure if that makes it, but okay, but if index was 3, we'd advance to node 3. If index was 4, we'd advance to node 4. And then all we're going to do is return the data stored in that node.
I have a question.
Yeah, go ahead.
So the item is the index element, right? So when it hit,
the item is the data stored in the node.
Okay, so like
array element is like an array element stores data. So,
okay.
So the index is just like a number. Go ahead. I'm sorry, what was your question?
So like, you know how when you do like int I is equal to 0, and then if it was an array, like array I, that I element is the number inside the array, right?
Right.
So that's what item is that number in the node list, right?
No, the item would be on the left side of the, like in an array, here, let me go here. So here, so like here, the item would be cat and the index would be 0. These numbers are the index. And this is
okay.
Does that help a little bit?
Yeah, and then so it would run until it hits null, and then it won't print out nothing after that.
Well, in this case, this loop here, because it's not going to go all the way to the end. It's just going to go, where am I? We're just doing index number of iterations. So like if index was 1, we would just, so the linked list could have like 100 nodes in it. But if index is 1, we'd only advance from the head to the node directly after head. So we're not iterating through the entire linked list.
Oh, okay.
We're not stopping it. That's it. Yeah, to iterate through the entire linked list, you'd have to, well, there are a couple of ways you could do it. But one way to do it is while pointer is not equal to null. Yeah, so we're already going part way. So let's say index was 1 here. Let's say index was 1. So you start there at the head. So let's say you start there at the head. And if index was 1, we're iterating 1 time. So if index is 1, So we'll just let index equal 1. So you start the pointer here, and then we iterate index number of times. So we will advance just one time. If index is 1, so we're gonna index. So we're just gonna move the number of times we advance to the next node is equal to index. So we'd actually would stop at this node. So if index was 1, we'd stop at this node, and we would return A. Right? Does that help, Marcos? Or
Yeah, thank you.
so yeah, so index, if it was an array, the index is what goes in, is what goes in the brackets, and the item would be is what's actually assigned to the array element. All right. So hopefully we'll get an assignment soon, and you can get some practice with this. Yeah. So yeah, so the index is what, the index is just the node number, and the item is actually what's stored in the node. Okay, so should we try? Okay, let's just try doing something here. Okay, so I did something a little, just based on a student's question last time I had this. We don't have to do that. Okay, so let's, okay, so we've added 2 items. It should be, first one is cat, and then dog is next. So dog, so the last one added, we're always adding at the end. Okay, so let's see if we can do this loop here. So for int I is 0, I less than, hello, I less than, the name of the array, the name of the linked list is list dot size. That's, I needed that for this loop here. And then I plus plus. And so let's see if we can go system dot out dot print line, and then list. Then we're gonna use our get method. Okay, so the first time we're gonna get what's in position 0. Well, the size is only gonna be 2. So we're gonna get, first we should get cat and then dog printed out.
So this linked list is basically essentially like a generic.
It's allowing us to use, well, it's actually allowing us, yeah, it's allowing us to use generic. See, like what's in the curly braces? Yeah, so we can actually put anything we want, like in the curly braces, instead of string, you can put any class name you want. I think that's where
Okay.
the generic, that's where the generic comes in. So we're making it
Okay.
really very general. So it's not designed specifically just for strings.
Okay. So like in the last example you were giving on the linked list.java, that dot item dot pointer or whatever, that's all just that library's syntax, right? So throw new dot next dot item, that's all linked list library syntax, right?
Well, yeah, but we're starting from scratch. I mean, we're actually writing everything ourselves.
Okay.
This is typical. I mean, but this is kind of the common things you see in linked lists, like pointer dot next, pointer dot item, like this loop here, 24 through 26. This is the way you loop through a linked list. You set pointer to head, and then to advance, then you have a loop where to get to the next node, you go pointers assigned pointer dot next.
Sounds good.
Yeah, so pointer is always the current node, and this is basically, I said, yeah, advance to the next node. Yeah, and this is really, and you'll see this, and if you actually look at any kind of code for linked list, you'll see something exactly like that. So there's some things that might be unique to Java, like that inner class, but there's a lot of bookkeeping here, like this add method. Oh, first you have to check to see if the size is 0, because you can't go, because if the size is 0, that means last is null. Okay, so you can't go, if last is null, you can't go last dot next. You'll get a null pointer exception. So first you have to make sure that head and last aren't null. So there's 2 cases: size is 0, size is not 0. So there's just a lot of bookkeeping with a lot of this stuff. So, but any other questions on this, or?
No, that's good. Thank you.
So let's go to the really, what about you, Jose? Any questions?
No.
Okay, so let's go to the really exciting part, one of the highlights of the course, and that's so exciting. I forgot the name. QuickSort. So QuickSort is I forgot if I put the files up. Okay, I'll put it up after class. Okay, so they'll be right here. Okay, so And I'll definitely do that. Okay, so QuickSort is actually one of the most widely used algorithms in computer science. And there's actually a survey taken out, it was 10 years ago or whenever, like, people were asked, like, what are your top 10 algorithms? What's the most important algorithm? So one thing I say in the last class, well, it's kind of it's not like asking people like, what's your favorite movie or something like that, because it's just a smaller universe of people to ask about algorithms. Not that many people know about algorithms. Like everyone's seen the movie. So, but anyway, so QuickSort is in the top 10. It's considered one of the top most important algorithms, top 10 in the top 10 algorithm of all time. And there's another one, if you ever take linear algebra, Math 254, you might learn LU factorization, which is used to solve which is a very common way of, it's something that's used in, it's used in every algorithm for solving a linear system of equations. And I'm sure your calculator uses it. So, I mean, but you don't know that, right? You don't have to know how your calculator is solving a system of equations. Okay, so let's get some motivation for QuickSort. So the one thing about QuickSort, it's really simple, right? Just like I think if you actually look at the code for merge sort, it's really not that long. I mean, you think like some codes are just thousands of lines. Considering how important an algorithm and it's used in production code, merge sort really isn't a lot at all. And the same thing with QuickSort. All these sorting algorithms, there really isn't a lot of code to it. So let's say we want to sort that array there. So G, B, D, A, C, whatever, all the, and I think there's 16 characters in there. And so what we're going to do, so this is an iterative algorithm, and we're going to start by putting G in its proper place. And everything to the left of G will be strictly less than G. Everything to the right of G will be strictly greater than G. And in this case, I know there's no duplicates. So one way it's easy to find out, just count the number of characters in this. Let's count starting from position 1, count the number of characters strictly less than G. Well, there's B, D, A, C, that's 4, and D is 5, B is 6, another B is 7, and then there's a D is 8. So the G would actually have to go in position 8, right? So in position 0 through 7, you'd have the 8 characters that are less than G. Okay. So one thing so in this case, I know that the G is going to have to go to position 8. So when we sort this, the G would be in position H. Okay. And so what's going to happen is you're going to put the G in position H, and then everything to the left of G, and you want to guarantee everything to the left of G is less than G, and everything to the right of G is greater than G. And once that happens, then you can sort everything to the left of G, and you can sort everything to the right of G. And it's done recursively. You keep, so this algorithm calls itself, we'll see, we'll look at the code a little bit in a minute. But let's just see how, okay, so it might just be easier just to look at this chart right here. So basically all I'm saying right here is so there's the goal. You're going to sort GD, this thing right here. I don't want to say it again. And we're going to put G in its proper place. So in all these quicksort problems, we're going to take what's in position 0 and put it in its proper place. Okay. I just want you to know some books like the Xi book, I actually used the Xi book last semester, and they don't start with position 0. They actually take the middle element. Some real kind of production code, they take 3 elements at random and then pick the middle one of those or something. I think it's something like that. But we're so actually, what element you're going to put in its proper place? There's all kinds of research done on that, which is the best element. But for us to keep it simple, we're not so worried about optimization or anything like that. We just want to learn the algorithm. So we're going to take what's in position 0, and the code that I'm using is actually on the Sedgwick website. Okay, so what we do is we start at I at position 1. So the I is going to start at position 1, the one directly after G, and then we're going to have another variable called J, and that's going to start at position T, which I think is 15. And what's going to happen, we're going to move I to the right until we find the first value. that's greater than or equal to G. There's no duplicate. So in this case, we're going to look for the first value greater than G. And it turns out to be the J at position 5. And then, okay, so we stop. Then we do the same thing with J. We move from, we start at the end and we go in, we go from right to left. And then the J, we look for the first value that's strictly less than G. Okay, so which happens to be the D at position 12. Okay, so we go from left to right, we find the first element that's greater than G. When we go from right to left, we look for the first element that's less than G, and then we exchange them. So we put all the elements, so we move from the right. So what we're going to do is on the right, we're going to move all the elements that are less than G to the left, and we're going to take, and on the left, we're going to take all the elements that are greater than G and move it to the right. And then we're going to put G in the middle. Okay, so so we stop at I equal to 5 and J equal to 12, and then we exchange what's in positions 5 and 12. And then you just continue that process. Okay, so let's just look at this example right here. Okay, so I typed this out, and so this very first one, that's the original array. And so we're going to scan this array. Okay, so, well, B is less than G, D is less than G, A is less than G, C is less than G. Oh, but J is not. So we stop our I right here. And okay, so then and again, we start that row 0, and we start at T. And we're gonna find the first one that's strictly less than G. T is not less than G. N is not less than G. Y is not less than G. Uh-oh, the D is. So we stop your J right there. And then what we're gonna do in the very first iteration, we're gonna exchange what's in position I and position J. So that's what happens. We exchange the D and the J. Now look what just happened, because we did a lot of comparisons. The code actually does a lot of comparisons. We actually compare one by one. Oh, is B less than G? Yes, it is. Go to the next one. Is D less than G? It is. Go to the next one, and so forth. And we're coming from the right. You go, oh, is T greater than G? Yes, it is. Go to the next one. Is N greater than G? It is. Go to the next one. So by the time we do the exchange, we know that everything here from 1 through 5 is less than G. And everything from J to 15 is got to be greater than G, right? So we're gradually building up the left side and the right side. So at this point, positions 1 through 5 are guaranteed to be less than G. And positions 12 through 15 are guaranteed to be greater than G. Now we still have to look at, what haven't we looked at? Positions 6 through 11. You have to look at every character. Until you do, you're not guaranteed that, all the small stuff is on the left and all the big stuff is on the right. So we just continue the process. So we started, where did we leave off? I at 5, but we put that D at position 5. Okay, so we start at position 6. We start at the first one on the left that we haven't looked at, and that's position 6. Okay, well, D is less than G, so go on. B is less than G, so we go on. Uh-oh, M is not less than G. I mean, M is greater than G. Okay, so the next time the I stops is now going to stop at position 8. That doesn't look like an I, does it? The I stops at position 8. And then we start here at 11. So we were going from right to left. We stopped at 12. Okay, so now let's just start again at 11. The Q is greater than G. The S is greater than G. The B is less than G. So the J stops at 9. They haven't crossed yet. Okay, so at this point, you exchange the values stored at A sub 8 and A sub 9, and then so the B gets put in position 8, M gets put in position 9, and now we're guaranteed that everything from 1 through 8 is less than G. Everything from 9 through 15 is greater than G. Okay, so now what happens here? So the J starts, if you can read my writing, let's just do this one more time. So the I stopped at 8. So the latest value of I is 8 and the latest value of J is 9. Okay, so now the I stops. So we start again, but now the I is 1, it starts at 9. Oh, there's an M here. Stop I at 9. M is greater than G. And now the J starts at 1. So the J stopped at 9 before. The J stopped at 9 before. So let's start at 1 to the left of 9, which is 8. Oh, what is there? There's a B, and that B is less than G. So we stop. So we stop at J equal to 8. So let's just say that again. Okay, so before I was 8, we made the exchange of B and M. I was 8 and J was 9. We start the process again. We start at I equal to 9. There's an M there. M is greater than G, so stop at I equal to 9. Okay, and then J had stopped at 9, so now let's make J equal to 8. And oh, there's a B there. B is less than G, so I just stays. So now J is 8. They've crossed. J is less than I. So when that happens, that's what guarantees. We've looked at every value, and when J is less than I, we stop and we exchange position 0 with position J. So that's what happens. This G here, that G in position 0 got all the way over here. So now that the G is, that B is in position 0 and the G is in position 8. And look at this, we're guaranteed everything to the left of G is less than G. Everything to the right of G is greater than G. So now we can sort the left half and we can sort the right half, and we can use the exact same process. Let's put this B in its proper place. And now, but now we've doubled the size of the problem. Before we had one array, now we have 2 pieces. Let's put this M in its proper place. We're not going through all of that again. I remember the very first time I ever taught this course, I thought, okay, we'll just sort the whole array. I go, no, I think it would just be awful for the students to write and for me to grade. So we're just doing one iteration of this. This is what we did is called partitioning. We partitioned the array so that G was kind of in the middle, and everything to the left of G was less than G. Everything to the right of G was greater than G. And the method returns the location of G, which is 8. The method always returns J. So let's, so stop me anytime that you ever want to talk, but so this stuff here, all these slides here, might be a little confused. Basically, I'm just explaining what I just said. So I'm not sure how useful it is. I mean, I was kind of looking at before class and I kind of go, what did I mean? Okay. But that happens a lot, to be honest. I look at my old stuff, I go, what was I trying to do there? Okay. This is the code for QuickSort. Well, this is the code for the sorting part, sorry. And then the partition part is the longer part. But let's just look at the sorting part. So again, the user, if they want to use QuickSort, well, they call some public method, and all they do is they pass in their array. And it's going to be an array of type comparable. So we don't even have to know that it's a type of comparable. We just have to make sure that our array is for a class that implements the comparable. And so if we were going to use this method, we don't necessarily know, we don't need to know that it uses QuickSort. We just use it, right? And we just assume it's going to work. Just like there's this built-in sorting method in Java called arrays.sort. We might have used it in Math 130, I can't remember. But it actually uses some variation of this QuickSort. It uses either QuickSort or merge sort, depending on whether you have an array of ints or an array of objects. But most people who use it don't know that, but they still use it. It still works. Just like I turned my car on and I have no idea what's going on. Okay, so the user uses this public method, public sort, and this public sort method then calls this private overloaded version. See, the number of parameters is different, and so low for our purposes, low is always going to be 0, and high is always going to be length of the array minus 1. Okay, so while low is greater than high, so when low is equal to high, that means you have an array of size 1, and it's automatically sorted. Okay, so so we're going to call that partition method the one that breaks the array up into 2 pieces, and we get its index. You know, where did that, like, where did the G go? Into position 8. So for our problem, we get an 8, and then what it says is, okay, now sort everything from 0 to J minus 1. Sort everything from J minus 1 to the end of the array, because what's in position J is in its proper place. Right? Basically, that's all it would be saying is, you know, sort, put the G in its proper place. So we can just, you know, so then you'd break, so first we sort the entire array, and then we would call sort, you know, 0 through 7, and sort 9 through 15. That's basically what it's doing. And look how short it is. I mean, it's just so elegant. I mean, these recursive methods are very hard to write, but it's really, okay, partition, sort the left, sort the right. And it's called divide and conquer. And you see that in a lot of algorithms, including the merge. If you actually look at the code for merge sort, it's in there. So, I mean, here it is, this widely used algorithm. Look, it's hardly any code. So I'd say at one time it didn't take a lot to become famous. Now, if you want to become famous in computer science, who knows? You have to, build the world's fastest computer or something. I don't know. Okay, so okay, it's more than just writing a few lines of code. Okay, so this partition method is what I talked about. This is the one that actually does the array transfer. I mean, the array exchanges. This right here, this is all V is always, for our purposes, V is always A sub 0. Right? This is the one, V is what we want to put in its proper place. It's the element at position 0. And this is actually what's doing the exchanges. And so this one here, this is how we move from left to right. It's saying and V is it's like for that problem, V would be like G. What's at position 0? So is A sub I less than what's in A sub 0? If it's true, increase I by 1. And you stop when you find, like for our problem, we stopped when we found a character greater or equal to G. And so this is what that first while is what moves you from left to right. The second while loop is what moves you from right to left. And you ask yourself, is what's in position 0 less than A sub j? And if it is, you subtract 1 from j. And if I is less than j, and after the 2 while loops are done, if I is less than j, you exchange what's in I and j. And then when I is greater than or equal to j, you stop and you exchange what's in position 0 and j, and you return j. And that's all we did in that example there. And we'll do a couple more examples, and I'm going to find some more for you as well. Let me just quickly say this. So on average, QuickSort takes n log n comparisons. So and there are scenarios where it takes up to n squared. Actually, a sorted array is one of the worst cases for QuickSort. A sorted array will take n squared comparisons. What do I mean by average? And then we'll go on to some of the worksheets. What do we mean by? This is a different version of this is kind of an optimization. I'm not going to talk about it, but this would be an optimization. The one thing about QuickSort, there's been all this research done how to optimize it. So this would be an optimized version if there's only a few different array values. But here I want to. What do I mean by the number of the average runtime? So let's say you had, let's say we wanted to sort, D, A, B. And then how many there's actually there's 6 different ways we could write this, combine this. You actually learn this in probability. So it could be DAB or DBA, or, ADB, ABD, or BAD, and BDA. So there's 6 different ways. And so let's say I then use QuickSort to sort each one of these. There's 6 of them. So I'm going to use QuickSort to sort each version. I add up the number of comparisons, the total number of comparisons for this version and version 2 and version 3, all the way through version 6. So I sort all these 6 versions of DAB, different combinations with QuickSort. Add up the number of comparisons involved and divide by 6. And that's the average. That's the average number of comparisons. So so one optimization for QuickSort is again, you're not sorting. If it's just 3 values, you wouldn't use QuickSort. Let's say it's like 1 million or something, and you're sorting. So some algorithms actually just randomly make exchanges to the array, and then applies QuickSort. And I guess you're more likely not to get one of the worst case scenarios. So anyway, but so QuickSort's widely used. Lots of PhD theses have been written trying to optimize QuickSort. So I wonder if the developer QuickSort knew what he was doing. That he probably didn't realize how famous his algorithm was going to be. So let's just open this. let's just try a couple problems. Hello, it's right here. Okay, so this first one's small. I have a typed version of all this, and I will post some more for you to practice on. Most students, I'd say, get this problem. Some don't. But maybe I sometimes always wonder it's because they don't study. Okay, that happens. Maybe we don't have time to study. So that's it. So we're going to put Q in its proper place. Okay, we're going to, so we always put what's in position 0 in its proper place. So both the I, so remember the I starts out at 1 and the J starts out at the very, all the way to the right. So initially I is 1 and J is equal to 1. And then, and so, okay, so I is, okay, so J is not great. I is not, let me say this. I'm having a hard time saying. So we stop iterating when I is greater than or equal to J, which is true. J is less than or equal to I, so we stop iterating. So we exchange what's in position 0 and position J. So we actually would just exchange M and Q and return 1. I'm pretty sure that's right. So the partition method should return 1. I did that. I didn't check. Is that right? Yeah, it returns 1. It always returns wherever the Q went. Yeah, so in this case, both I is 1 and J is 1. I is not less than J, so exchange what's in 0 and with position J. And you always return the last value of J. So let's try a couple more, students, of this interesting problem here. So it's kind of funny, these really small cases sometimes are the ones that are the hardest for me. Really, I think it does really make you think about the code. Because in this case, I and J start at the same character, which is kind of unusual. And of course, you wouldn't use QuickSort for any of these because they're too small. And that's the one thing about QuickSort. You keep breaking the arrays in half, and when the arrays get small enough, I think some codes will actually revert from QuickSort to insertion sort. Okay, so let's look at 2. Now note we're going to put the M in its proper place. We want to put that M in its proper place. The M is what's at position 0. So let's just do one iteration and then we'll look at the typed version. So we're going to put this M in its proper place. And then, I don't know why I didn't type all these in. G, 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 U, B. Okay. And so remember the I starts out at 1 and the J is all the way at the end. Okay, so look right away. Is what's in position I less than M? No, it's not. So we stop here at the S. That's the first one that's greater than or equal to M. Start from the right, as we go left to right. And so let's start at 11, and let's go from right to left and find the first one that's greater than or equal to M. And that turns out to be K. Is that right? No, it does not turn out to be K. Hello. Okay, it turns out to be U. Yeah, J, K, L, M. Okay, so, okay, I do know the alphabet sometimes. Okay, so it turns out to be U. Okay, so let's start here. So we started, okay, when we started from the right, right away, we saw S was greater than M. So we stop at I equal to 1. Okay, and now the I starts out at 11. Oh, but, oh, wait a minute. I'm sorry. I was right. I'm just getting tired here. Let's start this again. Okay, so we want to put M in its proper place. So we go from left to right. We stop at the first one that's greater than or equal to M, and that happens to be S. Okay, now let's go from right to left, and we're going to stop at the first one that's less than or equal to M, and that happens to be K. Yeah, so K is less than M, S is greater than M, and then we're going to exchange, right? All the stuff on the right that's less than M goes to the left. All the stuff that's greater than M that's on the left goes to the right. So we do this exchange. I only need to write one of these. F, and then this would be K. So yeah, we exchanged. This would be S. Probably hard to read. So let's just go to the typed version. It's hard to read. So you do this one exchange. You exchange 1 and 11. So let's just look at the typed one. Yeah, see, yeah. So so the first exchange, the first time I is 1 and J is 11. And yeah, so A sub 1 is less than M, A sub 11 is greater than M. Okay, so now, okay, so what's in position 1 is less than M, and what's in position 11 is greater than M. And now we continue. Okay, we start at 2, and we're going to look for the next one that would be strict, that'd be greater than m, and then it actually turns out to be the u. So the I would actually be 8. And we started, so we actually put something at position 11. So let's start at 10 and go to the left and find the first value that's strictly less than m, and that turns out to be f. So your j is right here. So your j would be 10. So now I is 8 and j is 10. So you exchange what's I, so you exchange I and 8. I mean, so you exchange 8 and 10, and so you exchange the u and the f. So now let's look what happens. So the f goes to index row column 8, the u goes to column 10, and now look what happens. Okay, so we made the exchange, and everything from 1 through 8 is strictly less than m, and 10 and above is strictly greater than m. But we're not done because we haven't looked at every array element. So let's just start this. Let's continue the process one more time. Okay, so we put something in column 8. So the I is going to start out at 9, and that B is strictly, no, the B is less than M, so we go on. So remember, we go from left to right. You're trying to find the first one that's greater or equal to M. So the I is going to start at 9. Oh, B is less than M. Oh, but not the U. So the I becomes 10. Okay, so now the J is going to, we just put something in position 10. So now the J starts out at column 9. And we see, oh, is that less than M? It is. We stop there. Okay, so J is less than I. When J is less than I, we stop. Or J less than or equal to I, we stop. And then we exchange what's in position 0 and position J. So we exchange the B and the M. And now we're guaranteed, let's look through 0 through 8, strictly less than M. And 10 and 11, strictly greater than or equal to, both 10 and 11 are both greater than M. So everything to the left of M is less than N. Everything to the right of M is greater than M. And now, once again, we can apply the QuickSort algorithm to the left side. Oh, let's put this let's put this B in its proper place. But we would only look through positions 0 through 8. And now let's put this U in its proper place, but we'd only look at positions 10 and 11. But we're not going to do that. So should we do one more unless there's any questions? And you actually just have to practice this yourself, my feeling. So the blank worksheets will be up there, so I'll find some new problems for you. I like this. Let's just stop at this problem and we'll do it. But the thing that, notice that we're going to put that E in its proper place, but there's 2 other E's. So a common error is not to stop. You stop at equality. And do I actually have I think it's actually in the algorithm. Oh, let's see the code here. I'm not making this up here. Okay, so where's it's right here. We're going less, so when do we increase I? When A sub I is strictly less than V. So if A sub I is equal to V, we stop. And the same thing too, when do we, as we move from left to right, when do we stop when V is strictly less than A sub J. So when V is greater than or equal to A sub J, we continue. So we stop at equality. So it's kind of a common error in these problems, and some students will skip over. We'll continue searching to the left or to the right if we get equality. Okay, so let's start in this case. Okay, so I is going to start out at 1, and J is going to start out at 12. And so we scan from left to right till we find the very first value greater than or equal to E, and that turns out to be the S. And we start at position 12, and we scan to the left until we find the first one less than or equal to E, and that turns out to be E. So a common error would be go all the way to B. So we stop at so we're going to stop at so we stop at I equal to so we scan from left to right, and we stopped at I equal to 2 and J equal to 7. Whereas a common error would actually just stop at J equal to 6. Now some people it's equal, then let's keep continuing. So we exchange what's in 2 and 7, right? So that E in position column 7 now is in column 2. The S in column 2 is now in column 7. And everything positions 1 or 2 are less than or equal to E, and 7 and above are greater than or equal to E. And we still have to inspect columns 3 through 6. Okay, so now we continue. So we just put something in column 2. So let's start in column 3 and continue the process. We'll move to the right until we find something that's greater than or equal to E. Oh, there's an E in column 4. Okay, we put in something in column 7. So let's start in column 6. Move to the right until we find a value less than or equal to B, E, and that's B. So now our I is 4 and our J is 6. So now let's exchange 4 and 6. So the B goes in position 4 and the E goes in position 6. So everything from 1 through 4 is strictly less than or equal to E, and everything 6 and above is greater than or equal to E. We still haven't looked at, but I is still less than J. We haven't looked at the value in position 5. Okay, so the I starts out at, we put something in position 4, so let's start at 5 and start this process. I will become 5 and we'll move to the right. Well, the Q is actually greater than E, so the I will stop at 5 in the next iteration. Okay, and then we put something in column 6, so let's just put the, so we'll start the J out at 5. We continue to the left until we find something less than or equal to E, and that's the B here. Okay, so we stop at I equal 5, J equal to 4. Oh, J is less than I. Let's do the exchange. So we exchange the B and the E. And so you return what's in J. We return, the partition method returns 4. So the next time around, you'll sort 1 through 3. You sort 0 through 3. You sort 0 through J minus 1, and you sort J plus 1 all the way to the end. So I know that was kind of fast, and I think you just have to practice it yourself. So I will put, the worksheets are up there, and I'll put some more up there. But are there any questions right now? But I think the basic idea, we have the basic idea. The small values are moved to the right, and the large values are moved to the left. Any questions right now? And I just want to, if you look at any other sources on this, just remember that the thing about QuickSort, it's not standard. As I said, we always pick the what's in position 0 to put in its proper place. I'm saying other books, other sources, you might start elsewhere. Like some places start in the middle, like the Zybook starts in the middle. That's why I use the Zybook. I think starting at 0 is pretty common. I couldn't find any videos last semester on QuickSort starting in the middle. And I think I know some good QuickSort videos, and I'll look for it and put it online. But any questions right now? I'm going to stop sharing then. I'm going to stop the